Hey guys, it's Mr. Luneski. We're going to go over the Chapter 25 notes here together, so just kind of follow along, pause it if you need to, rewind if you need to, kind of get you through paired samples today. Paired data is usually when we have groups that represent the same people or the same subjects. We oftentimes think of experiments. Usually we think of like before and after kind of results. It's not always before and after, but typically it is. It's used often in the medical fields and personal health fields of study, fitness, things of that sorts. So we're just going to kind of go through sort of our 4 steps and what sort of changes in Chapter 25. So because the 2 sets come from the same person, a before and an after, we can't really say that the data is independent. So when we state our conditions, the independent condition gets a little iffy. And we can't really call this one sample a one-sample t-test, so instead we call it a paired t-test. So it is important to specify whether you're doing a one-sample t-test when you just have one group and not paired data, or if you do have paired data. So one-sample t-test is kind of what we were doing back in Chapter 23. Just as a couple little reminders, when pairs arise from an experiment, that is a type of blocking, and when the pairing comes from an observational study, that is what we call matching. So blocking and matching are kind of the same sort of concepts, but remember, blocking is specific to experiments, matching is specific to observational studies. Remember, observational studies is when you aren't interfering, you're sort of just watching what happens. Key thing to remember here is that this is a difference between sets of data, and so when you calculate the differences, you're only going to use that particular set of data. And we're going to get into that as we talk about our 4 steps here. So our 4 steps: hypothesis, condition, mechanics, conclusion. What's changing? So in our hypothesis with the null and the alternative, instead of just saying mu, or mu1 minus mu2, we now have to say mu sub d. You do have to specify what mu sub d is. So typically our null and our alternative, are going to look, something like this, saying that there is no difference, saying that there is a difference. You do have to specify, though, that if it's mu, and you might see it look like this, before and after is equal to mu sub d. So you sort of have to specify what that is in your hypothesis box. The conditions. The random condition is the same as before. The independence condition sort of doesn't really exist. We can say that the subjects are independent of each other, therefore the differences are also independent too. You should specify and say that they are paired. To say like the data that we have listed is paired, therefore we can say the differences are independent, something along those lines. The nearly normal condition, we're focused on the differences, so you really have to draw just one histogram, and that histogram is going to be your mu sub d list. The 10% condition is the same as before. We can say that the subjects are less than 10% of all people that exist, and then we'll use a student's t-model and a paired t-test. The mechanics are pretty much going to be the same. We're going to run a t-test, but you're going to run it on the list of differences. And typically you're going to store that in list 3. And then the conclusion, all of that stuff stays the same before. Reject, fail to reject. And then a confidence interval, we can do a t interval. Again, that would be on list 3. Alright, so let's quickly take a look at our example problem here. So we have resting heart rates. 10 people volunteered to test an exercise device advertised on television by using it 3 times a week for 20 minutes. The resting pulse rate in beats per minute were measured before the test began, and then again after 6 weeks. Results are shown in the table. Is there evidence that this kind of exercise can reduce resting pulse rate? So we're looking at, can it reduce the resting pulse rate? And then if so, how much? That's telling us use a confidence interval. Alright, so first thing that you want to do, let's just go ahead and state our hypothesis first. And so for the hypothesis, we want to say that mu sub d equals 0, and mu sub d, well, let's take a look. If mu sub d is equal to mu of before minus the mu of after. If we're trying to figure out if it's reducing resting pulse rate, that means that these numbers in the after column would be less than the before numbers. And so if these numbers are less, then this number minus this number should be greater than 0. So mu sub d is greater than 0. So what do we know here? We know that the null states that there is no difference in the mean pulse rates in beats per minute for the before, and here's where you can say mu sub b, and the after, mu sub a, if we want to call it that, results. The alternative states that the after results are lower than the before results. Alright, so now we want to check our conditions. We can assume that the people are randomly selected, even though it says that they were volunteered here. We probably want to say, maybe not that they were randomly selected, but that they were sort of a representation of the people involved, of the population. We can assume that 10 people is less than 10% of the population, since our data is paired. So this is kind of what you want to say. Since our data is paired, we assume that the differences between each person is independent. And if we check the histogram of the differences, it appears roughly symmetric and unimodal. Therefore, conditions are met. We can use a t-model and a paired t-test. So let's take a look at the histogram. So on your calculator, pull that in division for you guys. I have list 1 and list 2. List 1 is the before, list 2 is the after. So then typically what we want to do here is up in list 3, you can call that L1 minus L2. And if you hit enter, it actually fills that list in. And so now this list, list 3, that's our sort of mu d. This is what we're going to run all of our tests and things off of. So to look at that histogram, we'll go to second y equals, we'll turn the stat plot number 1 on. Let's just change that to list 3. And then zoom stat. And so again, that really doesn't give us a kind of a good representation of what we're looking for. So if I hit zoom 3, zoom out a little bit, kind of get a better idea of what the graph looks like. So when we were zoomed in real tight like that, it actually looked like these three things were the same height, but that's because it went taller than what we were expecting. So always make sure you zoom out if you feel like you're not getting a good picture of the graph. Okay, so back to here. So all of our conditions are met, so that's all good there. For our mechanics, so what are some things we need to list for mechanics? How does this change? We need to list our n value, which is 10, and then basically everything else that we have to list comes from running the test. And so we can say x bar of d, we can say our t value, we can say our p value, and alpha is not specified, so we'll just assume 0.05. Okay, so let's run the test. So back on your calculator, if you go to stat and then you go over to tests, we're going to run a t-test, and then remember we have the data, and we have the data inside list 3. So for mu, we're going to make that 0 because we're saying, there is no difference, so there is a difference. Our list is in list 3, frequency stays as 1, and we are testing, is it greater than 0? And so I go to calculate. And if you take a look at our numbers here, t is 3.5, our standard deviation is 2.53, 2.8. So let's go ahead and write these numbers down. So our t value was 3.5. Standard deviation was 2.53. X bar was 2.8. P value was 0.00. Whoops, 3. Not 0. Alright, and then there's our alpha level. So what's going on with our p-value? Our p-value is low, therefore the hoe must go. And so we can say this is our conclusion, that since our p-value is less than alpha, we will reject the null. There is statistically significant evidence to support that the resting heart rate in beats per minute is lowered after using the device. They also asked us the question, if so, how much? So just as a reminder, on your calculator, when you go to stat, you go to test, you go to number 8, t interval, and we run that on list 3. 95% confidence interval is acceptable. And then we get this number here as our difference. So 0.99 and 4.6 roughly. And so we can say we're 95% confident that the resting pulse rate is reduced by a difference of 0.99 and 4.6 beats per minute. Alright, that is all I have for you. Thank you for watching.